Hi, and welcome to the lecture on the greenhouse effect. Today we're going to do two things. First, we're going to use multiple models of the greenhouse effect, different ways of showing this phenomenon on the planet, to understand how air temperature can change on Earth. And second, we're going to learn how to make predictions about changes to Earth's air temperature in response to different natural and human events. And in fact, we're going to use these models that I'm going to show you to help you make these predictions. So first, I want to relate your responses to previous assignments to the greenhouse effect model. I'm very excited that many of you already have an understanding of the greenhouse effect, and I want to help you build this understanding to a more complete scientific model. This is a representation of the greenhouse effect that many people have. I actually have done research on people's understanding of the greenhouse effect, and this is something that's very, very common. So in this model, the idea is that there's a sun, it emits energy, that energy bounces off the Earth's surface, and some of it goes to space, while some of it bounces between the Earth's surface and a layer of greenhouse gases that act as a barrier, and some of the energy bounces off the Earth's atmosphere. This is a partially correct model, but it's not the complete model. And what I want us to learn today is why this model results in predictions related to Earth's air temperature that are inaccurate. So what's the problem with this model? Well, this model would predict that if you have more energy bouncing off of the Earth's surface and then off of this boundary layer, the more energy we have bouncing, the hotter the Earth's atmosphere should be. The hotter the air temperature, the higher that temperature. But in fact, the more energy that bounces off the surface, the more energy goes into space and the colder Earth's atmosphere becomes. So this model, while predictive, doesn't predict phenomena in the right direction. So I hope today you'll learn more about the greenhouse effect and understand why this model is close but not quite right. First, let's just have a quick understanding of air temperature. So what is temperature? Temperature is actually the average kinetic energy of molecules. So by kinetic energy, we mean the energy of motion. Air molecules in general are always moving. Unless they're at absolute zero, the coldest possible temperature they could become, molecules are moving. They're not sitting still because temperature is the measure of kinetic energy. So if those molecules have any kinetic energy, they have some temperature. The question I have is, do molecules move faster in cold or warm air? So in some cases, molecules will be moving like this, and in other cases, molecules will be moving like this. Which ones move faster? Well, it turns out that air molecules move faster in warm air because they have more energy. So the higher the kinetic energy, the higher that energy of motion, the more those molecules are moving, the higher the temperature. That's what we mean when we use the word temperature. How fast are molecules vibrating and whizzing around? For your own reference, molecules in solids are also moving. They're just fixed in position and moving a little bit. Molecules in liquids are moving. They're just moving a little bit faster. And molecules in a gas, like our air, like our atmosphere, are moving a lot. They're whizzing all over the place. Another piece of background that you should be familiar with is that of light energy. So when we talk about light, we're actually talking about a very particular kind of electromagnetic radiation. This graph shows different kinds of electromagnetic radiation. You don't really need to understand the graph completely, but what I want you to understand is that light energy, the energy that we see with, is actually just a very small piece of the electromagnetic spectrum. We're also going to be talking about infrared energy today. So I want you to notice that infrared energy has just a slightly different wavelength than light energy. We don't see in the infrared spectrum, but we do see all of these colors. So that's pretty important to know, and it's important to know that light energy has a different wavelength than infrared energy, for our purposes, is the same as heat. Soldiers can use special infrared seeing goggles to see an object, a human being, an animal, something that emits heat, by using those goggles to see in the infrared spectrum. Your car heats up on a really hot day because energy from the sun goes into the windshield, it gets absorbed by the dashboard and by the seats of the car, and then it gets re-emitted as infrared energy. The wavelength of the energy changes after it's absorbed, and then it stays in that heat energy wavelength when it's emitted. So your car gets very, very hot, not because the energy that comes from the sun is this heat energy, but because the energy that is emitted by the interior of the car after the solar energy is absorbed is that heat wavelength. So we're going to use several different methods to explain the greenhouse effect, and I hope by the end of this lecture you feel comfortable with it. There is a really nice animation of the greenhouse effect, which is available through University of California in San Diego. I've taken some components of this animation and I've animated them in this lecture for you. So the greenhouse effect can be explained first by realizing that there is a sun, that the Earth orbits around, and that the Earth has an atmosphere. Most of the energy at the Earth's surface comes from the sun, and the energy that comes from the sun is called radiation or solar radiation. This energy is electromagnetic and it's visible with just a little bit of infrared and ultraviolet radiation in it. You're probably familiar with ultraviolet radiation from thinking about wearing sunscreen to protect you from cancer. Ultraviolet radiation has very little role to play in the greenhouse effect, and we won't talk about it. The infrared radiation that comes from the sun is very, very small. Again, most of the energy that comes from the sun is visible. This incoming visible solar energy, it has a short wavelength, and it passes through the atmosphere fairly unaffected until it reaches the Earth's surface. Some of the energy that hits the Earth's atmosphere will be reflected back into space, and some of the energy that reaches the Earth's surface will also be reflected back into space. The Earth's surface absorbs much of the energy that comes from the sun, converts it into infrared energy, and re-emits it as this infrared energy or heat. Some of it ends up going back into space, as seen here. Some of that infrared energy is absorbed by gases in the atmosphere, gases that we call greenhouse gases. And that energy is then re-emitted in all directions by these greenhouse gases. The energy can be reabsorbed at the Earth's surface and then re-emitted in all directions to again either be absorbed by greenhouse gases or lost to space. Let me show you what these gases do. These gases absorb the infrared energy, re-emit it in all directions as heat energy, back towards the Earth's surface or back out into space. And the re-emission of this energy back towards the Earth's surface means that this energy is kept within the Earth's atmosphere. Because the energy is in the Earth's atmosphere, and again, temperature is a measure of the average kinetic energy of molecules, which means that the more energy the molecules in the atmosphere have, the warmer the atmosphere will be. This is the greenhouse effect. We can see what's happening if we zoom in on these molecules, and we can see that these greenhouse gases are absorbing this infrared energy, and then they're re-emitting it in all directions, some of it back down towards Earth's surface, some of it in the atmosphere, and some of it out to space. So now I'd just like to walk you through some other representations of the greenhouse effect. I have found that students learn best when you represent the greenhouse effect multiple ways. So I'd like to do that for you now. We have a sun and an Earth. This is not to scale. The sun is actually much, much bigger than the Earth, but we want to focus on what happens in the Earth and in its atmosphere. Energy comes from the sun. It's mostly visible energy with a little bit of UV and a little bit of IR, ultraviolet and infrared. It's mostly visible. When it reaches Earth's surface, some of it is reflected out to space. Some of it is absorbed by the Earth. This absorbed energy is then re-emitted as infrared energy. Infrared energy, if it encounters a greenhouse gas in the atmosphere, will be absorbed by that greenhouse gas and then will be re-emitted as infrared energy, some of it out to space, some of it back down towards the Earth's surface through the atmosphere. Another way to represent the greenhouse effect is with a box and arrow model. In this model, we also focus on how energy is transformed and moves. We think about, though, the 4 places where this energy is moving or transforming: space, the sun, the Earth's atmosphere, and the Earth itself. One of the most important aspects of this model are greenhouse gases. These greenhouse gases are dispersed through the Earth's atmosphere. The previous model didn't really show this. This model does. Greenhouse gases also absorb infrared energy or infrared light. Visible energy comes from the sun, as does a little bit of ultraviolet energy and some infrared energy. This energy can pass into the atmosphere, mostly unaffected, and eventually it all reaches the Earth's surface. Some of this energy is absorbed by the Earth's surface, and when that happens, it's converted into infrared energy. Some of that infrared energy will be absorbed by greenhouse gases in the Earth's atmosphere. That infrared energy that is absorbed by greenhouse gases in the Earth's atmosphere will be re-emitted in all directions, some of it into the atmosphere, some of it back towards Earth's surface to be reabsorbed or reflected, and some of it will be re-emitted to space. And finally, a cartoon model of the greenhouse effect. In this model, we see energy being emitted by the sun. Some of that energy will reflect off the top of the Earth's atmosphere and go into space. Most of the energy will move through the atmosphere. When solar energy in the visible spectrum interacts with greenhouse gases, there's really no effect, or little effect. Some of the energy that reaches the Earth's surface will be reflected out into space, and some of that energy will be absorbed. After the energy is absorbed, it is reflected back into the atmosphere as infrared energy. Now, infrared energy, if it happens to encounter a greenhouse gas, because the atmosphere is made up of greenhouse gases and other gases, if that energy happens to encounter a greenhouse gas, it will be absorbed and then re-emitted in all directions. Some of the energy emitted at the Earth's surface will move out to space. Now I'm going to write out the model of the greenhouse effect that contains the components of the greenhouse effect that I think are most important for you to understand to be able to reason with this model. I know that we repeated ourselves in this lecture, but I wanted you to get it several different ways so that hopefully the model becomes something you feel comfortable with and something that you are able to work with. Solar radiation enters the Earth's atmosphere. That solar radiation was emitted by the sun. This energy is generally not absorbed by greenhouse gases and so proceeds towards the Earth's surface. The Earth's surface absorbs the solar radiation and converts it into infrared or heat energy. Some of the solar radiation that reaches the Earth's surface will be reflected back into space. The heat that is generated when the Earth's surface absorbs solar radiation will be re-emitted by Earth into the atmosphere. Any greenhouse gases in the atmosphere that encounter this solar radiation will absorb some of this heat, and then the greenhouse gases re-emit this heat in all directions. The average temperature of the atmosphere will therefore go up. The more heat is absorbed and the more energy is emitted by those greenhouse gases. Something I want us to remember is that the atmosphere is almost completely made up of nitrogen and oxygen. 99% of the atmosphere is nitrogen or oxygen. Nitrogen makes up over 3/4 of the Earth's atmosphere. Nitrogen and oxygen are not greenhouse gases. Greenhouse gases are a small component of the other 1% of gases that make up the Earth's atmosphere. So that means that greenhouse gases are very, 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 very rare. They're not that common. And because of this, if we change the composition of greenhouse gases in the atmosphere, we increase or decrease the number of greenhouse gas molecules in the atmosphere, then we change the probability that infrared energy emitted by the Earth's surface will encounter and then be absorbed by a greenhouse gas. If this energy is absorbed by a greenhouse gas, then the average energy of the atmosphere has gone up, which means that temperature will increase. A few facts that you should have in your mind, and I'm going to give you a few minutes to reflect on these. Carbon dioxide and methane are the two most important greenhouse gases, though of course they're not the only ones. Carbon dioxide is thought to be responsible for about half, or 50%, of the warming that we've seen in the last 150 years. Methane is another greenhouse gas. It is 25 times more powerful than carbon dioxide, which means that it absorbs infrared energy about 25 times better than carbon dioxide does. And it may be that methane is the most important gas for warming in the next 50 years. So let's think about how carbon dioxide and methane are made and used. Carbon dioxide is made, that is, put into the Earth's atmosphere through volcanic activity, burning oil in our cars, or coal in our furnaces, or natural gas in our furnaces, or in our electric power plants, through the removal of trees or the burning of trees, through animal respiration, through our breathing, and through the manufacturing of cement, which is quite interesting since humans make so many buildings. Carbon dioxide is used or taken out of the Earth's atmosphere through photosynthesis, by trees and algae, and by limestone deposition in the oceans. Methane is made or put into the Earth's atmosphere in landfills, wetlands, and swamps, through livestock, because of the gas that the animals emit, through coal mining, as we're growing rice, and through the burning of feces, as done in some countries, or trees, often for heat or cooking. Methane isn't really used or taken out of the atmosphere by very many processes. It's pretty much, once it gets in there, it's going to stay there. And it takes a very long time for it to break down in the atmosphere, which means that once it's there, it's going to stick around. So just reflect for a second on the various ways that carbon dioxide is put into the Earth's atmosphere, the various ways that it's taken out of the Earth's atmosphere, and the various ways that methane is put into the atmosphere. Let's think about how we can reason with the model of the greenhouse effect to understand how we can change Earth's atmospheric temperature by changing the amount of infrared energy that goes into the atmosphere. Because the more infrared energy we have in the atmosphere, the warmer the temperature will be. And the less infrared energy we have in the atmosphere, the lower or colder the temperature will be. If we think about the greenhouse effect, there are several very important pathways. There's a pathway of energy from the sun. There's a pathway of energy from the sun moving through the atmosphere. There's the sun's energy being absorbed by the Earth's surface and then re-emitted as infrared. And then there's the infrared absorption by greenhouse gases. If we increase an input, then the output will also increase. If we decrease an input, then the output decreases. And similarly, if we slow down one of these processes that occurs during the greenhouse effect, we'll slow down the output of infrared energy. And if we speed up a process, we'll speed up the output. So let's put this into practice. We're going to figure out how each of the following processes would change Earth's air temperature. And when I say air, I mean the same thing as atmosphere. First, let's think about how energy output from the sun decreasing would impact Earth's air temperature. So imagine energy output from the sun decreases. Let's reason with this model. I like to use the cartoon model. You're welcome to use any of the models that I've shown you today. If energy output from the sun decreases, that means that there will be less solar energy coming in. That means there will be less energy absorbed and transformed to infrared at the Earth's surface, which means there will be less infrared emitted by the Earth's surface, which means there will be less infrared absorbed by greenhouse gases. If there's less infrared absorbed, there will be less infrared emitted by greenhouse gases, which means ultimately there will be less infrared energy in the atmosphere. Air temperature will go down. So if energy output from the sun decreases, air temperature will decrease. Let's look at the second example. Imagine we have a number of natural disasters, storms, hurricanes, floods, that result in us having to make more buildings and therefore produce more cement for construction. What will this model allow us to predict about how that increase of cement production would cause an increase or decrease in Earth's atmospheric temperature? If we produce more cement on Earth, what will we do? Cement production produces carbon dioxide. Remember, that's a greenhouse gas. Solar energy input will stay the same. The energy absorbed and transformed to infrared at the Earth's surface also stays the same. The amount of infrared energy emitted by the Earth's surface stays the same. However, because there's now more carbon dioxide in the Earth's atmosphere, there's a higher probability of that emitted infrared being absorbed by greenhouse gases in the atmosphere. The more infrared energy absorbed by greenhouse gases, then there's more infrared energy emitted by greenhouse gases, which means there's more infrared energy in the atmosphere, which means air temperature will increase. I hope this has been a very useful lecture for you to help you understand the greenhouse effect, and I look forward to seeing how you do on your discussions and homeworks.